Welcome back. So for this part of the lecture, we are going to be talking about nuclear stability. We are also going to see how to write transmutation reactions. So I told you that any radionuclide is the element trying to become stable due to the repulsions of the protons inside the nucleus. And they do that by releasing some particles like positron, electron, neutrons, proton, even energy like gamma energy. So how do we know which elements will tend to do that, and how do we know which elements are going to be stable? The more stable an element is, the least the possibility that it will have isotopes, because the stable one will probably be the one on the highest abundance. The more unstable is, the more possible isotopes it can have. So let's define nuclear stability. So like I said before, once you have more than one proton, they're gonna repel each other. So they're gonna have repulsions. And those are gonna happen because the nucleus contains a lot of them and they're super concentrated, super dense, so they're very close to each other. So what keeps them together? What keep them together inside the nucleus, we call that the strong nuclear force. And we know that neutrons are important on that regard. So the neutrons are going to be somehow related to the strong nuclear force, but that out of the scope of this course. So the ratio of the neutrons and protons is an important factor. So if you have one proton for every one neutron, that's going to be very stable. At least when you don't have that many protons. So that only happens with elements with atomic number less than 20. So any element all the way to calcium, they probably going to have a ratio of almost 1:1, which makes them very stable. And those are the traditional elements that we see all around us most of the time. So this neutron to proton ratio is very important. And like I told you before, atomic number less than 20 or equal to 20, calcium, with a neutron to proton ratio of 1:1, those are going to be stable elements. As the nuclei get larger, they will have to have more protons. More protons because it's getting larger, and to keep all these protons together, you're going to have to need more neutrons. And then the ratio of 1:1 begins to disappear. So you're going to need more neutrons as you go past number 20 to make them stable. So we have collected all this information in this chart, and we call this the belt of stability chart. And as you notice, up till 20, so these are my neutrons. This is the number of neutrons. So the number of neutrons and the number of protons up till 20, they fall right on the line. So those are very stable. As we begin going above 30, we're going to notice that the elements, since we're increasing the number of protons to neutrons, for example, element number 30, we have close to 38 neutrons. So we start seeing that the 1:1 ratio is beginning to be lost, and we start seeing a deviation from the line to get stability. So that's where the belt of stability develops, going away from the straight line once you go to atomic number 20 or above. So 1:1 ratio, very important, but that's only going to happen elements 20 or below. All the other elements, we are gonna see some other trends that allow us to say that they are stable. And what we're gonna see is that sometimes through experimentation we know that any element with this amount of protons is going to be stable, or with this amount of neutrons. So that's something you should have on your notes, because I don't believe this is going to be on your packet. So those are, in general, based on what we know from experiments, those are going to be very stable. Also, if the number of protons and neutrons tend to be even numbers, that also going to be a stable isotope, more than the odd numbers. So you will be looking for those trends. And this is something just showing you what happens. So if they are unstable, it's going to be a play where uranium can go become thorium, then palladium, then back to uranium. So it's a back and forward game. And once you have uranium, it can go back to thorium again, Ra, I don't remember what that is, and radon, polonium, and lead, and back and forward, a gain of back and forward between these three. And eventually, most of the radioactive elements are going to go all the way to lead. And lead is very stable. So let's apply these trends that we just saw. So any elements atomic number 20 or below, with a ratio of 1 to, they're going to have a ratio to 1 to 1, so they're very stable. We have the magic numbers. So if they have that number of protons or that number of neutrons, they're going to be stable. Or if they have even number of protons and neutrons, that's going to be also stable. So with that said, let's do some work. So determine whether each nuclide is likely to be stable, and state your reasons. So titanium, 48, mass number 48. So titanium is going to be atomic number 22. So this is going to be titanium 48. Even number. So that may be stable. Let's see the ratio. So protons equals 22. Neutrons equals 26, because 26 plus 22 is 48. So that's our mass number. So almost 1 to 1, and they're even numbers. Are those also some of those magic numbers, 22 and 26? No, it's not of the magic numbers. No, they're not the magic numbers, but they are even numbers. So we're not saying that they're super stable. We are saying that they're more stable if I was comparing them to something with odd numbers. So you can say that this is most likely a relatively stable isotope because the amount of protons and neutrons are even numbers. That would be one way to say that. Tin 102. So we're going to have tin. It's going to be 102, and the atomic number is going to be 50. So once more, we're seeing even numbers. So that's going to be my reason to say that this is relatively stable. Even numbers, 102 and 50. So that means I'm going to have 50 protons and 52 neutrons. This is really, really close to 1 to 1. However, that's super stable if the atomic number is less than 20. This is 50, but almost 1 to 1, even numbers. So I would say relatively stable. What about the next one? Chromium 63. So chromium is going to be 24. So right there, we can see that we're not going to have even numbers. So 24 protons, neutrons is going to be 30, 39, right? So not that stable. You don't have even numbers. The ratio is not 1 to 1. And 24, it's 24, one of my magic numbers. For the protons, no, it's not. So I would say this is probably not stable. A and C are stables. What about D? Yttrium 88. So yttrium 88. Yttrium is going to be number 39. So once more, you can see that it's going to be not an even number. So protons equals 39. Neutrons is going to equal 49. 18. Yep. So definitely not stable. Both of them are odd numbers. So not stable. So that's a very rough approach to decide if your nuclide is stable or not by using those rules that we just saw. Let's check something else. Let's check yttrium. 39 protons, 49 neutrons. Let's check the belt of stability, 39 and 49. So 39 and 49. Let me clear this a little bit. See if it falls in there or not. 39 and 49. So 39 is going to be around there. And 49 is going to be around here. So according to this, 39 protons and 49 neutrons, that kind of falls within the belt of stability. So that's kind of a stable isotope. So our better way to know if something is stable or not then will be to use the belt of stability. Our better way to compare to others then is these rules here. This tells us if it's more stable or less stable compared to something else. So let's try another one on the belt of stability. Let's try the chromium, 24 and 63. Sorry. Not 24 and 63. 24 and 39. Protons and neutrons. 24 protons, 39 neutrons. So let's see. 24 protons will be around here somewhere. So 24 protons, 39 neutrons. So this one is obviously outside the belt of stability. So chromium is going to be not stable. So going back to this, I would say this one, due to the belt of stability, this one is stable. So check first the belt of stability. If you had to compare between two that are unstable, then you know which one is more stable between those two. If you are comparing between two that are stable, then you can find out which one is more stable by using these rules and these rules here. So with that in mind, go ahead and do that daily work. And once you do that, do this one. And this one is talking about half-life, but it's not asking you to do any calculations. So which one will have the longer half-life? What does having a longer half-life means instead in terms of stability? And then you can use the rules to answer that question. So a different concept, nuclear transmutations. So transforming one element into another element. We usually do that by colliding particles. A particle like an alpha, beta, neutron, protons colliding with a nuclide, like uranium-235 or something like that. Another way to do that is by taking two atoms and smashing them together. And we usually do that on particles accelerators. This is a aerial view of one of them. So look at this building, and look at the size of this. So those are huge projects. There was actually one probably before you were born. They were building one in Waco, not more than an hour from here, and it was almost finished. It was supposed to be so awesome. It was supposed to bring so many jobs to this area and so much progress and knowledge. And back then, the Soviet Union dissolved, so the Cold War ended, and the government didn't see the need to continue advancing science, and they left it almost complete. They abandoned the project. They took out all the funding. So I don't know if you are able to, but it would be nice to go there and see if a group can explore that, because it was almost done and when they killed the project. So those are extremely important. France ended up building one, and they have been taking giant leaps on the knowledge of this. And a lot of the new elements have been discovered on places like that. So kind of sad when the politicians get involved with science. So how can we use that? Well, before we said that, any element after uranium, we call those the trans-uranium elements. So any element after number 92, they were discovered because they were smashed in something like that. So they were bombarded with neutrons, and the neutrons created new elements that up till that moment didn't exist. So we created those elements after element 92, after uranium. Once we go past 110, those were definitely colliding atoms of one element with atoms of other elements, and just to see what came out. And every so often we saw something new that had never been seen before by a human being. And if we can repeat it, and we can actually define the properties of it, then it makes it to the periodic table. Within the last 3 or 4 years, we have added like 3 more elements to the periodic table. When I was doing my undergraduate degree, there was only 103 elements on the periodic table. Today, we're up to 118. So we keep discovering elements. So don't be surprised if 10 or 10 years from now, we're probably all the way up to 130 or something like that. And the beauty of that is that every time we discover something new, sometimes we can do marvelous things with them that we couldn't do before. So how can we write those equations when that happens? So this one, for example, so this one here is showing nitrogen being bombarded with an alpha particle. Remember, this is an alpha particle. So if we bombard nitrogen with alpha particles, we create an isotope of oxygen, and in the process, we release a proton, which could be represented like I showed you before, like a proton, or like what we said it is, a proton. So something with one proton and one neutron is just hydrogen, right? And we can write that 2 different ways. We can write it like I showed you earlier, where we're taking care that the atomic numbers, 9 on the left side equals 9s on the right side, and the mass number, 18 on the left side equals 18 on the right side. Or we can write it like this, where we're going to show the reactant on this side, the product on the other side, and in between parentheses, the particles that were used. An alpha particle was part of the reactants, and a proton was produced as part of the products. And here is just the representation of using the symbols that we already know. So that's how we can write a transmutation reaction. Nothing new, exactly the same thing we did before. Now we have a shorthand version on how to write something like that. So let's practice a little bit. Let's do this one. A breeder nuclear reactor is a reactor in which non-fissionables, so non-fissile, so it cannot be broken apart, it's converted into fissionable, or broken apart in a new element. So what we're saying is that we're going to take uranium-238, atomic number 92, and we're going to make it into plutonium-239. Let me go find the atomic number for plutonium. So that's going to be number 94. So a breeder, a nuclear reactor, is a reactor in which non-fissionable uranium-238 is converted into fissionable plutonium-239. The process involves bombardment. So we're going to bombard uranium-238 with neutrons. So we are bombarding it with neutrons to form uranium-239, to form the process involves bombardment of uranium by neutrons to form uranium-239, which then undergoes two sequential beta decays. So this is the final reaction. So what it's telling us is that uranium-238 is bombarded with a neutron to make uranium-239, which is a balance equation, right? Yes, it's a balance equation. So let me see if I can do this on the short notation. So uranium-238, which is my reactant, producing uranium-239. So I'm doing that with a neutron. And there's nothing in there, so I'm just gonna change that to uranium-239-92. So bombardment with a neutron produces that. However, it tells us that after that, the 239 undergoes two sequential beta decays. So uranium-239 is going to decay by a beta decay, which is -10. So this will have to be 93, 239, and 93 is gonna be neptunium, NP. So that will be uranium 92, 239, producing, that's a beta particle, so you can say a beta particle producing Neptino 239. And then we're gonna take the Neptune 239. And it's going to undergo the other beta decay, creating 94, 239, and 94 is going to be, let's see, plutonium. And that's what we create at the end of that. So we began with 238 and ended up with plutonium 239. And we did that by bombarding uranium 238 with a neutron. The product of that decay by beta decay, and the product of that, two consecutive beta decays, gave us the plutonium 239. So that's how you can follow that sequence using nuclear chemical reactions, a transmutation. Let's see if we see that on here. So uranium 239, no, that doesn't show in there. So that's a different sequence of events. So with that said, you should be able to do this daily work. And the main focus is going to be on the actual the balanced nuclear reaction. Do not worry much about the shorthand notation. And once you do that, you should be understanding better nuclear stability, what information to use, the belt of stability, and the numbers, the magic numbers, and the even number versus the odd numbers, and so on. So you can predict nuclear stability. You should be able to kind of once you do the nuclear stability, you should be able to figure out what particle is being emitted or is decaying by what particle. And that's going to take you, and that's going to relate to the neutron to proton ratio, where 1:1 is the most stable one. So that's it for this part. When you come back, we will begin talking about kinetics of nuclear reactions, where we're going to talk about the half-life. And we're going to solve problems with half-life for nuclear reactions or nuclear decay. So until the next one, I will see you soon. Take care.